Okay, so here we are with our last section of chapter 14, ready to close the book, so to speak, on this chapter of aldehydes, ketones, and chiral molecules. Hopefully things are going well so far. You've got a good handle on aldehydes and ketones. Okay, so then if we've discussed the aldehydes and ketones, I guess that leaves the chiral molecules before we can end our chapter here. And these, much like the hemiacetals and acetals we talked about in our last section of this chapter, will be very important when we think about biological molecules, in particular the carbohydrates that we just mentioned, but also amino acids, as we'll see later on. So we have a few different types of isomers possible, right? There's the structural isomers that have the same formula but different bonding arrangements. And if we look at a molecular formula as simple as C2H6O, we've got a couple different ways we can draw that thing, right? We can have ethanol, which has an OH, a hydroxyl group. It's an alcohol. Or we could draw dimethyl ether. We could have that oxygen in between, bridging those two methyl groups, and that's an ether functional group. Very different behavior, vastly different boiling points, for instance, but again, the same overall molecular formula. If we look at stereoisomers, now we have atoms that are bonded in the same sequence. So we're not making and breaking bonds. There's no way to turn ethanol into dimethyl ether without breaking bonds apart, moving that oxygen, and reforming bonds. For stereoisomers, you can do that. You can make them in a different way because of how they're arranged in space, not because of what's bonded to whom. So as a result, stereoisomers are molecules that are known as non-superimposable mirror images. There was the other type of geometric isomer where we talked about cis or trans when we were focused on the alkenes a few chapters back, and that's another type of isomerism that we're not discussing here, nor are we discussing the structural isomers. It's the stereoisomers that are our focus. Okay, so chirality, that's a mouthful, right? And maybe not sure how to pronounce that. I believe I'm pronouncing it correctly, right? I've heard it more than a few times in my career as a chemist. And molecules are chiral when their mirror images cannot be completely matched. They're said to be non-superimposable. As an example, your hands are chiral. So if you try to superimpose your hands, if we have either, back of the hands up or palms up on both hands, we can't put them together palm to palm. That doesn't work. We've got to have the backs of the hands, the little fingers, they don't align. They're mirror images. So when the mirror image of an object is identical and can be superimposed, it's known as achiral. So our hands are chiral. Actually, the word chiral has chir or chir, as you might have seen in chiropractic, for instance. That's someone who works with his or her hands. Also through French, where we soften it up a bit, we get serge, and surgeon is someone who works with his or her hands as well. So both of those going back to that idea of hands as being chiral, non-superimposable mirror images. Okay, so if we look at the image here, we see a left hand, again, palm up. We see a right hand, palm up, and they don't match. But if we look in the middle where we have the right hand with its back to us, its mirror image is the palm side of a left hand, right? So again, this is what we mean by chirality. It's a handedness. Our hands clearly have it. Well, some molecules do as well. Now here's some other images, and we can see gloves. Obviously, since our hands are chiral, our gloves are chiral too. You normally buy a pair of gloves that has a left hand and a right hand glove. If we look at baseball bats there, well, those are achiral, right? Yeah, they align perfectly. You don't have to buy a left-hand bat or a right-hand bat, although a left-handed batter would hold it differently than a right-handed batter would. If we look down below on the left, we've got two glasses, and they're achiral, right? They're perfectly superimposable. They're not non-superimposable mirror images like our hands or our gloves. And then finally, just like our hands are chiral, well, our feet are chiral as well. And that's why we need a right shoe and a left shoe. We can't buy a pair with two right shoes and expect that to work for us. So when you have substances, features in the case of the human body that are non-superimposable, like hands or feet, well, the clothing that goes on those hands or feet would also need to be chiral. Now, as wonderful as these pictures are, and as we move into pictures of chemical compounds, it's really in building these things in 3 dimensions that it starts to make sense. So hopefully we're able to pick up an inexpensive used molecular modeling kit, but failing that, if you can get some, I don't know, some toothpicks and clay or something like that to just give yourself a chance to play, be a kid again, get out the Play-Doh and use the different colors and try to keep them together with bonds made of toothpicks or something else, and you'll get a chance to see how these things look in 3 dimensions and hopefully make some real sense of it rather than trying to rely on these 2D representations. Okay, so this is the organic chemistry section, chemistry of carbon, right? So if we're looking at carbon, we'll know if a carbon atom is chiral or achiral if that carbon atom has 4 different groups or atoms, then it's chiral. It's going to have mirror images just like your hands. When we have stereoisomers that cannot be superimposed, they are called enantiomers, and that's how we know that we have a chiral center, is that we're going to get 2 enantiomers for every chiral carbon in a compound. All right, so if we look at the mirror images of bromochloroiodomethane, we can align the H and I atoms, which place the Cl and Br atoms on opposite sides. So if we keep the H and the I up and down relative to one another, notice that the Cl and Br have swapped, and that's because they're mirror images of one another. But when we rotate them, there's no way to superimpose those mirror images. We get the problem that if we have it all aligned correctly with the H and the I, then the chloro group and bromo group are not aligned correctly. They're non-superimposable mirror images, and therefore they're known as enantiomers. They cannot be superimposed on each other. Now you might think that every mirror image is going to give you a non-superimposable partner that would therefore be chiral, and that's not the case. If we look here, notice if we have dibromochloromethane, we now have a situation where the mirror images don't look the same. If we look at the mirror images on the left-hand side, we have a chloro group off to the left, and on the right-hand side, we have a bromo group off to the left. But if we rotate these species without breaking any bonds, just a simple rotation, we can get the bromo groups to align, the chloro group to align, the hydrogen to align. Everything works. And notice that we didn't have 4 distinct substances. In the bromochloroiodomethane, we had 4 different groups. We had a hydrogen, a bromine, a chlorine, and an iodine. Here we have 2 of the same groups. We have 2 bromo groups, and therefore we would not expect this carbon to be chiral. Instead, just a simple rotation gets us the same structure over again. This is an achiral carbon. Now I know what some of you are thinking out there. You're thinking, well, I'm going into nursing, and what does this have to do with biology or biochemistry? Why are we talking about all this chiral, achiral stuff? Well, because biologically speaking, many molecules of biological importance are chiral molecules. So molecules in nature, just like molecules we can synthesize in the lab, have mirror images sometimes that are not superimposable. And oftentimes in biology, one stereoisomer has a vastly different biological effect or no biological effect compared to the other enantiomer. So this is very important here. We see the plus and the minus carbone, or levo and dextrorotary, the L and the D there indicate the handedness. We saw that earlier in this chapter in a previous lecture where I just sort of ignored the letter L or D there. But here we're going to address it. It has to do with that carbon, right? That carbon there with the star on it, the bottom carbon of the ring is a chiral carbon. It has 4 different substituents. 3 of them are carbons, but they're carbon groups that are different if we go beyond. So don't feel like, oh, well, it's bonded to 3 carbons, it can't be chiral, unless those 3 carbons are identical. If they're 3 methyl groups, then you're right, they can't be chiral. But if they're 3 carbon groups that are different and unique, then you can indeed be chiral, and that's oftentimes how chirality happens in organic molecules. look at the left form, the levorotary carbone is spearmint. The right form, the dextrorotary carbone, is caraway seeds. So vastly different flavors and odors because of that slight difference, that non-superimposable mirror image relationship. All right, before we go any further with this idea of chirality, let's pause for a learning check. In this learning check, you're asked to identify each of these structures as chiral or achiral. So stop the video here, make those assignments, and start it back up to check your work. Okay, hopefully it didn't take you very long to make the correct determinations. For A, we have 4 different groups on that central carbon, and therefore it's a chiral carbon. We have a hydrogen and a chloro group. Those are clearly different from each other. But then we have 2 different carbons, right? We have a carbon of a methyl group and a carbon of an ethyl group. And although that carbon in the center is bonded to 2 other carbons, those 2 other carbons are parts of different groups. A methyl group carbon is different than an ethyl group carbon, and therefore we do have 4 unique bonding partners, and we are indeed a chiral carbon, at least the central carbon. The other carbons, the CH3 has 3 hydrogens, the CH2 has 2 hydrogens, so those could not be chiral carbons, but that center carbon in A is indeed chiral. For B, it should be even easier. We have 4 different groups, 4 different atoms for that carbon in the center to bond to. It bonds to a chloro group, a chlorine atom, a hydrogen atom, a bromine atom, and a carbon atom of a methyl group in this case. For C, C is achiral, and the giveaway there on that central carbon is that there are 2 hydrogens. Whenever you have 2 of the same group, it is achiral for that particular carbon. So be on the lookout for that, and if this didn't go so well, then please do try some additional practice problems where you're looking for identifying chiral carbons or achiral carbons, and if you still have trouble, please do reach out to me for some help. Now, as a beginning student in organic chemistry, it's probably tough to do this all in 2 dimensions. These are 3-dimensional concepts. But one thing that organic chemists have at their disposal is called a Fischer projection. And a Fischer projection is a 2D representation of a molecule. It places the most oxidized group up at the top. Then you use vertical lines for bonds that go back, use horizontal lines for bonds that go forward, and it tries to take that 3D molecule and represent it reasonably well in a 2-dimensional plane. Okay, so looking at these Fischer projections for erythrose, notice we put the carbonyl carbon up at the top. That's because it's the most oxidized group, right? Just like our rule said. And then we've got 2 chiral carbons in this particular substance. So the 2 chiral carbons that meet at those T's, those crosses there, we have the carbonyl carbon can't be chiral because it has 2 bonds to oxygen, and the final carbon there has 2 bonds to hydrogen. So it's those 2 middle carbons that we don't show because it's a skeletal structure type arrangement, but they have 4 different bonding partners. In a case where we have multiple chiral carbons, we have to have a rule. And so in this case, the rule says that the designation as a D or L isomer is determined by the position of the OH group attached to the chiral carbon farthest from the carbonyl group. So the reason we have the L isomer for the left-handed version that we call L-erythrose is that furthest chiral carbon from the carbonyl has the OH group on the left side. If we look at the D-erythrose, notice that same position, that same carbon, we have the OH group on the right side. So that's our convention, and that's what those L's and D's mean. L is for levo, which is left, and D is for dexter, which is Latin for right. So that's how you do it, and that's how you determine the left and right projection from a Fischer projection. Okay, so here we have another learning check. In this learning check, you're asked to indicate whether each of the following pairs of Fischer projections can or cannot be superimposed. So for A and B, go ahead and determine whether they can or cannot be superimposed. And then once you've made those determinations, start us back up. We'll see how you did. Okay, hopefully you were able to make these correct determinations. For A, they cannot be superimposed. These are left and right-handed versions of each other. They are indeed enantiomers. It is a chiral carbon, and the way we know that is by looking at that center carbon, which isn't shown. It's the point where the lines cross. It has 4 distinct bonding partners, right? Carbon of a methyl group on the right, and then a carbon of an alcohol containing carbon group on the top, and then a hydrogen and a bromine. So we have 4 distinct species, and therefore we have a chiral carbon, cannot be superimposed. For B, notice we have 2 bonds off that center carbon to hydrogen atoms. So because we have the same species bonded twice, we are not chiral, and therefore we can be superimposed because they are just simple rotations of one another. So there we have it. Hopefully you were able to make those correct determinations. If not, please do try some more. It does take a little while to get the hang of these Fischer projections. And finally, if you're still having trouble, then please reach out to me for help. All right, let's try one more learning check before we leave this portion of chapter 14 where we're discussing chiral molecules. In this learning check, identify the following as a D or L isomer. So there we have it. Notice the most highly oxidized group there is shown as a CHO. That's really the carbonyl of a aldehyde in this case, and that's the most oxidized, right? The alcohols are not as oxidized as the carbonyl, so that's in the correct orientation. If you remember the rules, you should have pretty minimal trouble with this learning check, but go ahead, stop it here, make the determination of D or L, and then start it back up to check your work. Okay, so if you remember the rule, we've got lots of chiral carbons, by the way, right? All of those carbons that we see there, aside from the starting carbon, the carbonyl carbon of the aldehyde, or the ending carbon that has the CH2OH, those are your only achiral carbons. In between, you have 1, 2, 3, 4 chiral carbons. So how are we going to determine if this is a D or an L isomer with all those chiral carbons present? Well, the way we'll do that is by looking at the last carbon, the one furthest from the CHO, the aldehyde group. We're looking for the OH group off of that last chiral carbon, and it is to the right on our Fischer projection, and therefore this is the D isomer. So hopefully you remembered that and you were able to get it correct. If you either got it incorrect or aren't sure, you happen to guess but aren't sure why it's correct, please do try some additional practice problems on this topic and certainly reach out to me for help. Otherwise, hopefully everything's coming together for you and you're ready to move into the next chapter.